In the second lesson of Unit 6, we will focus on parallelograms and specifically key properties that will hold in all parallelograms. So parallelograms, rhombuses, rectangles, squares, these properties today are true for all of those figures. We're going to focus on specifically the sides and the angles, any relationships that can be discussed between those. And then secondly, we're going to discuss diagonals. Along the way, we're going to do a few proofs for three of our four theorems. We're going to see a couple examples, and basically the key here is that we can work through the proofs explaining why these relationships exist, why these properties are true today. So the first theorem that we have is Theorem 6.1, and it states that the opposite sides of a parallelogram are congruent, that the opposite sides of a parallelogram are congruent. Now, we probably believe this already when it comes to rectangles and squares and rhombuses, but this is true for all parallelograms. And the proof of this we actually did back in Unit 4, in the lesson where we did CPCTC, or where we applied the definition of congruent triangles to show that we had opposite sides in our parallelogram congruent. So we've actually already done this proof back in Unit 4. Essentially, what we want to do is prove that these opposite sides are congruent to each other. Now, I'm going to just draw one of these diagonals in through any 2 points. There exists exactly one line, so I can draw that segment right there. We are given that this is a parallelogram. This magical symbol here means that this ABCD is a parallelogram, meaning that the opposite sides are parallel to one another. So if this is a parallelogram, then the opposite sides are parallel. Essentially what we will do is we will show that these alternate interior angles on alternate sides of the transversal between these parallel lines are going to be congruent, that these alternate interior angles are congruent, and then therefore this reflexive side also being congruent means that these triangles are congruent. All right. So our proof here is a little angle side angle. We're going to say ABCD is a parallelogram. This is given information, and this means that AB is parallel to CD, and BC is parallel to AD. This is by the definition of a parallelogram. Which again, I'm going to just draw the symbol for a parallelogram, which looks like a parallelogram. Next, I'm going to state that those alternate interior angle pairs are congruent. Now, I have to use three letters. I can't say angle B is congruent to angle D and angle B is congruent to angle D, because that doesn't make much sense. I need to here say angle A, B, D is congruent to angle CDB. And I'm going to say that angle ADB is congruent to angle CBD. This is by the alternate interior angles theorem. So step 1, step 2, step 3. Step 4 is the reflexive side, BD congruent to itself. Therefore, the triangles are congruent. Now notice the way that I've written this. ABD is congruent to CDB, meaning that AB and CD are congruent, and meaning that DA and BC are congruent. So my last step is going to be to show that these sides are congruent. AB is congruent to CD, and BC is congruent to DA by the definition of congruent triangles. All right, so Theorem 6.1 states that the opposite sides in a parallelogram are congruent. We can apply that CPCTC to say that now these opposite sides are congruent. We will use this to create algebraic equations and then find the values of our variables. We'll have a situation like so, where we are told that PQRS is a parallelogram, and our job is simply to solve for the variable. We're not told anything else other than that this is a parallelogram, but we know now, because of Theorem 6.1, that this segment is congruent to this segment, and therefore the lengths of those sides are equal to each other. And so we're not going to necessarily say, you know, QR is congruent to PS by Theorem 6.1, therefore the length of QR is equal to the length of PS by the definition of congruent. Instead, we're going to start with the length of QR, 3x minus 15, is equal to the length of PS, 2x plus 3, so that we can create, so that we can solve now this equation. 3x minus 15 is equal to 2x plus 3. If I subtract 2 x's from both sides, and then I add 15 to both sides, it tells me the value of the variable. In some situations, you may be asked to plug that variable back in, substitute that value of x, and then find the lengths of the segments. We are not going to be doing that today. But this is how we would use that, applying Theorem 6.1. Our next theorem is to think about how these angles relate to one another, namely that the opposite angles are congruent to each other. But before we do that, we're going to explore a smidge, talking about some key vocabulary. First of all, consecutive angles are angles of a polygon that share a side. And so when we are talking about a parallelogram, the consecutive angles are essentially same side interior angles. In fact, when Mr. Hibbett was in geometry class, back in the 90s, back in 1995, in the fall of 1995, we called our same side interior angles consecutive angles. And so the same concept holds here, that these angles in a parallelogram are consecutive angles, and that these angles are consecutive, and these angles are consecutive, and these angles are consecutive. Essentially, they are same side interior angles. All right? We've got parallel sides cut by transversal, and those consecutive angles are supplementary because of the same side interior angles theorem. All right? So in this case, the x plus y would equal 180 would be our equation. Okay? And so we would use that in this situation. Here we have a parallelogram, and our job is to find the measure of angle S. Well, we don't have to do too much work here, and there's not too much thinking involved, but we would recognize that the measure of angle R plus the measure of angle S must equal 180. And that is not something that's new to this unit. This is because of the same side interior angles theorem. And if I know the measure of angle R, then I can use that to find the measure of angle X. All right? And use a calculator as needed. I hope that I subtracted correctly, although sometimes I've been known to have an error here or there, but I think that we did a very good job. All right? And so do not make this a difficult situation. You're simply acknowledging that the consecutive angles in a parallelogram are supplementary, meaning that they add up to 180 degrees. Their measures add up to 180. Here's another situation. Given this parallelogram, find the values for x and for y. Well, we would know that we've got two different equations to wrestle with. I've got an equation that involves y's and x's, and I've got an equation that just involves x's. So we want to make sure that we can attend to these in whatever way, shape, or form we are required to. So first of all, this is set up so that we would have y plus 7x is equal to 180. Well, this is not very helpful because I don't know what y is, so I can't find x, and I don't know what x is, so I can't find y. So this equation is not valuable to me at this moment. However, this other situation, these are consecutive angles. And so we're going to be able to acknowledge that we have 7x's and 8x's that are going to add up to 180 degrees. All right? So we have 7x's and 8x's make 180, which means that 15x's make 180. Again, sorry for the handwriting. You guys know that it is my lot in life that I can't write correctly. But anyway, we combine our like terms. We divide by 15. We find out that x is equal to 12. Now we can use this to backtrack and attempt to do our best work to find the value of y. And so we want to make sure that we do that calculation correctly, and then that we, after we plug in the value of x, we subtract that from both sides to find out that y is then going to equal 96. Okay. So here is why we wanted to explore this. This is actually going to lead us into the Theorem 6.2, which is going to tell us that the opposite angles in a parallelogram are congruent. Now, when I say opposite angles, you're like, so opposite, like what does opposite mean? Well, if this angle and this angle are in opposite corners of the parallelogram, then they are considered opposite angles. This angle and this angle are opposite angles. So if you want to think about this a couple different ways, essentially we can use the congruent supplements theorem, or its converse here, to say angles that are supplements of the same angle are congruent to each other. Or we can actually model this in this case to find out that y is equal to 96, and 8 times x, or 8 times 12, is also equal to 96. So these are going to have the same measure. Essentially, we don't need to work this as a proof per se, like we did on on Theorem 6.1. We can do that, but essentially what we have is if these are supplementary and these are supplementary, then angles that are supplements of the same angle are going to be congruent to each other. I will show you that proof of Theorem 6.2 here, if you are curious. However, if you don't want to use something from Unit 2, and in case instead you want to use a whole process from Unit 4, Theorem 6.2 states that the opposite angles in a parallelogram are congruent. The opposite angles of a parallelogram are congruent. That's Theorem 6.2. And our proof is going to be very much the same way. And I'll save you the heartache of us having to actually work this out. But the same proof that we had before. In this parallelogram, we know that these alternate interior angles are congruent. With these parallel sides, I know that these alternate interior angles are congruent, and therefore, with that reflexive side, we have ourselves a pair of congruent triangles using angle, side angle. Now, that being said, by CPCTC, or by the third angles theorem, we would say that this angle and this angle are congruent to each other. I think that the third angles theorem actually makes it a lot shorter. If we say, hey, these are parallel, therefore these angles are congruent, these angles are congruent, then we could just use the third angles theorem to say that the angle at A is congruent to the angle at C. Now that only tells us about one pair of angles. We would have to do basically all of those same steps again, showing again that we have a different diagonal drawn, diagonal AC. We still have parallel sides. We still have a different pair of alternate interior angles and another pair of alternate interior angles congruent. And then we can either use angle side angle with the reflexive side and then CPCTC, or we could use the third angles theorem to say that the angle at B and at D are congruent. Essentially, I think that there are many logical approaches we could take to showing that the opposite angles in a parallelogram are congruent, and these were just 3 of those approaches. But of course, we want to be able to use that. We're going to be using this to create algebraic equations, all right? That's the name of the game in this unit, is let's understand the properties so that we can apply those properties. If we've got congruent sides, then set their lengths equal to each other. If we've got congruent angles, then set their measures equal to each other. And this, let's make this as easy as possible. This is a parallelogram, supposedly, and so we're going to find the value of y here. We're going to recognize that angle F is congruent to angle H by Theorem 6.2. That means that its measures, their measures are equal by the definition of congruent. We're not actually going to write those first 2 steps, but that is the logic that lets us create this equation. 3y and 37 is equal to 6y and 4. All right? Once we have our actual equation created, the math is not too terribly difficult. We'll subtract 3y's on both sides. We will subtract 4 on both sides. We will divide by 3 on both sides to solve for the value of y. All right, now we don't have to write out our whole second column like we would have in our proofs unit or back when we did some work with algebra in the end of Unit 2. But we could say, hey, this is from Theorem 6.2. This is the definition of congruent. Here I did substitution POE. Here I subtracted on both sides APOE. Here I subtracted on both sides again APOE. Here I divided on both sides using MPOE. We could give that, we don't need to. All that I care about is that you do and show this work. All right, so please, so that you can find the highest level of success and that you can demonstrate for me a fullest understanding, not just tell me what y equals, but do this work. If you want to do the other, that's fine, but you don't need to. Start here with the equation and go from there. If you're having trouble with this and you're not doing this, then I'd say maybe start creating these expressions first and then work from there. Okay? Again, the task is doable. Create the equations, solve the equations. If you mess with the algebra here and there, it's not the end of the world, folks. All right, but if you are careful to create the equation, I pretty much promise you that you're going to do a fantastic job. All right, we could then plug in the value of y to find the measures of each of the angles. I'm not concerned about that right now, but that is something that you could do. All right, theorem 3 of 4 that we're going to do today, the diagonals of a parallelogram bisect each other. This one is a little bit interesting because this is going to require that we do a little bit of extra work, okay? So this is, I know, maybe not the most fun, but essentially what we would be required to do in this case is actually draw in these diagonals. And then essentially what we're going to do from there is go ahead and show what we know, what we have insofar as the triangle congruence relationships. All right, and this one is a little bit tricky for us. We will know that if I'm looking at these two triangles, I know that this angle and this angle are congruent by the alternate interior angles theorem. I know that this angle and this angle, that those are congruent. And then I also know that this side and that side are congruent because the opposite sides in a parallelogram are congruent. All right, so if those sides are congruent and those angles, then that means that these two triangles right here are congruent by angle, side, angle, side, angle, which means that their corresponding parts are congruent by the definition of congruent triangles. And if those parts are congruent, then that means that these segments did indeed bisect each other if they're being cut into this part congruent to that part and this part congruent to that part. I'm not going to work out that full proof right now, but that essentially is maybe the quickest way that we would go about doing that. Say that these angles are congruent by the alternate interior angles theorem. These sides are congruent by theorem 6.1. These angles are congruent by the alternate interior angles theorem. These two triangles are congruent by angle, side, angle. And then therefore their parts are congruent by the definition of congruent triangles. And therefore AC and BD, the diagonals, bisect each other by the definition of bisect. So this one is probably the one theorem that we will forget about this lesson. And so we'll be fine with the opposite sides being congruent, we'll be fine with the opposite angles, but the diagonals bisecting each other is one of those things that we tend to forget, or that students tend to forget. So if that happens, that is okay. But what we're going to do with that is actually some fancy pants algebra. And so by fancy pants algebra, I mean we're not going to do Unit 1, Unit 2 Algebra 1. We're going to do like Unit 7 Algebra 1. All right? We did a little bit of this in the last video in Lesson 1. And here is where we're going to have to be very careful with our algebra skills. All right? And then we're almost done here. All right? About 3-4 more minutes. If these diagonals bisect each other, then I know that x plus 1 would equal y. I would also know that 3y minus 7 is equal to 2x's. So the funny thing about this, ladies and gentlemen, is that I know what y equals. Y is equal to some number plus 1. But not just any number, it's x. And you know what? There's an x over here, and there's a y over here. So I can use what y equals from this equation in that equation. If I told you that y equaled 6, you would plug 6 in here and you would find x. If I tell you that y equals 7, you'd put 7 in there and you'd solve for x. If I tell you that y equals x plus 1, sometimes our brains stop working there, right? We forget about that pre-algebra, algebra 1 work, but I'm going to take 3y's minus 7 are going to equal 2x. But in place of the y, I'm not going to put the number 6 or 7 or 5 or 12 or whatever it is. I'm going to put the expression of x plus 1. All right? This is what y equals. Y is equal to x plus 1. So really, when I say 3y's minus 7, I mean 3x plus 1's, or 3x plus 3 minus 7, is going to equal our 2x's. All right? Or in this case, 3x minus 4 equals 2x's, or the opposite of 4 is equal to the opposite of x, and so x is equal to 4. Once we know what x is, we can use back substitution. Plug it back in, up there. X plus 1 equals y. Oh, that's not x, that's 4, because x equals 4. And so now we know what y equals. This is not witchcraft, it's Algebra 1. And we want to make sure that we do a good job of trying to remember and practice those skills. This will be the hard part to this lesson. And it makes it, because this algebra is hard, sometimes folks want to skip these items or skip over this content. And really what I want to do is I want to push you. I want to make sure that you are ready for Algebra 2 next year. It's coming up faster than you know. One more thing, and that is Theorem 6.4. This one's a little silly. It seems like a little bit of a waste of time, but we are going to use this and apply this in a couple different ways coming up, specifically in Unit 8, but there's some other things that we're going to do with that in the meantime. Basically, this is a little bit strange, but if you have 3 or more parallel lines, and those parallel lines are separated in such a way that they're cutting off congruent segments on the transversal, then this means, all right, so if that happens, that's the hypothesis, if these 3 or more parallel lines are cutting off congruent parts of a transversal, then that means that they are going to cut off congruent segments on every transversal. That doesn't mean that this is congruent to that. It means that if these are congruent, then these are congruent. All right? So if I've got something like all these parallel lines, and I'm saying that this is congruent to this is congruent to this, then no matter what I do, and no matter which line I draw, if I draw it like this, then this segment is congruent to this segment is congruent to that segment. If I draw it in a different color here, if I draw it like this, then this segment is congruent to this segment is congruent to this segment. All right? They're going to have the same length. You can actually try this if you'd like. On your lined paper that you're taking your notes on, those blue lines on your paper are, except for the very top and the very bottom, are equidistant. All right? They're equally separated. And so if you were to take a ruler and you were to draw a diagonal across multiple blue lines, you would see that each of those parts are congruent to each other. There's not really a ton that we're going to apply with this right away. The only example that we have is basically saying, well, hey, if these lines are all parallel, and this is 2, and this is 2, and this is 2, then if this is 2.5, we know that this will be 2.5, and this will be 2.5. So I can find out that this is 5 units big, that this is 7.5 units big, but each of these parts are going to be 2.5 units long. Not a huge, not a very useful thing for us in the immediate future, but it is something that we will be applying here in the near future. All right, easy questions, but limited application for us in the immediate future. All right, and so that, folks, is the lesson. That got us to about 20 minutes. Sorry for a longer video, but the goal here is that we can not just know what those properties are, know what those relationships are, but understand why they're true. So in summary, the opposite sides in a parallelogram are congruent. The opposite angles in a parallelogram are congruent. The diagonals in a parallelogram bisect each other. And if a set of parallel lines is cutting off equal segments in a transversal, then it cuts off equal segments of every transversal between those parallel lines. Please come to class with questions.